If you are over 60 and your sleep has changed, if you fall asleep without difficulty but wake between 2 and 4 in the morning with a mind that will not quiet, if your legs feel restless the moment you lie down, if the deep and restorative sleep of earlier decades has been gradually replaced by something lighter, more fragmented, and less refreshing, there is a specific biological explanation for that pattern. It is not stress, it is not aging in the general sense, and it is not the absence of melatonin. A 2012 controlled clinical trial measured the sleep architecture of elderly adults with exactly that pattern: early waking, fragmented sleep, nocturnal restlessness, using polysomnography, the gold standard of sleep measurement. What the intervention was and what the results showed contradicts what most people managing insomnia after 60 are ever told. That trial and the 5 interlocking biological mechanisms behind its findings are what this video is built on. The first thing to understand is that magnesium is not simply a mineral. It is a cofactor, a molecular enabler, required for the proper function of over 350 enzyme systems in the human body. Among those systems are the precise biochemical pathways that govern both the synthesis of sleep-promoting neurotransmitters and the regulation of the nervous system's ability to shift from activation into rest. Magnesium is required for the production of serotonin, the precursor molecule from which melatonin is synthesized in the pineal gland. It is required for the proper function of gamma-aminobutyric acid, GABA, the brain's primary inhibitory neurotransmitter, the molecule responsible for quieting neural activity and permitting the transition into sleep. And it plays a critical role in regulating the NMDA receptor, the glutamate pathway that, when chronically overactivated, keeps the nervous system in a state of low-grade hyperarousal, the biological equivalent of a mind that cannot stop running. Now, consider what happens after 60. Research published in Nutrients in 2018 identified a convergence of factors that conspire to deplete magnesium specifically in older adults. Intestinal absorption of magnesium declines with age. Renal reabsorption, the kidney's ability to reclaim magnesium before it exits in urine, becomes less efficient. Many of the medications most commonly prescribed to adults over 60, including proton pump inhibitors, diuretics, and certain cardiovascular drugs, further accelerate magnesium loss. And dietary intake, already marginal in most Western populations, rarely compensates. The result is a state of subclinical deficiency, insufficient for cellular function, yet invisible on a standard serum magnesium test because the body will strip magnesium from bone and muscle tissue to maintain serum levels within an apparently normal range. But what comes next is the part that most researchers did not initially anticipate. Because magnesium depletion does not simply affect one sleep pathway. It quietly disrupts 3 distinct and interlocking biological systems simultaneously, and the interaction between them explains why insomnia after 60 so often feels categorically different, more resistant, more pervasive than the sleep difficulties of younger decades. Mechanism 1. The GABA receptor failure. Gamma-aminobutyric acid, GABA, is the nervous system's primary brake. When GABA binds to its receptors on neurons, it opens chloride ion channels, hyperpolarizing the cell membrane and reducing the likelihood of that neuron firing. It is the mechanism by which the brain transitions from the alert, active state of waking into the quieted state necessary for sleep onset. Magnesium is an essential cofactor in the GABA-A receptor complex. Without adequate magnesium, the receptor's sensitivity to GABA is reduced. The braking signal becomes weaker. Neurons that should quiet down at night continue to fire. The subjective experience of this is precisely what older adults with insomnia so frequently describe. A racing, circling mind that refuses to settle, a body that feels physically tired while the brain remains lit. A study published in Neuropharmacology in 2011 demonstrated that magnesium's interaction with GABA receptors is not incidental, it is structural. Magnesium ions physically modulate the receptor's configuration, and depletion measurably reduces inhibitory tone across the entire central nervous system. The third mechanism on this list is the one that will surprise you most. We are almost there, but first, Mechanism 2. Mechanism 2. Cortisol dysregulation and the HPA axis. The hypothalamic pituitary adrenal axis, the HPA axis, governs the body's stress response and its regulation of cortisol. In a healthy circadian rhythm, cortisol peaks in the early morning to promote wakefulness and declines steadily through the day, reaching its lowest point in the late evening to permit sleep onset. In magnesium-deficient adults, this pattern breaks down. Magnesium normally acts as a physiological brake on the HPA axis, limiting the secretion of corticotropin-releasing hormone from the hypothalamus and adrenocorticotropic hormone from the pituitary. When magnesium falls below functional thresholds, this inhibitory influence is lost. The HPA axis becomes hyperreactive. Cortisol secretion rises, particularly in the evening hours, precisely the window when it should be at its lowest. Research published in the Journal of the American College of Nutrition in 1994, one of the foundational papers on this relationship, established that magnesium depletion produces measurable increases in urinary cortisol metabolites, confirming elevated HPA activation. More recently, a 2010 study in magnesium research demonstrated a bidirectional relationship. Stress depletes magnesium, and magnesium depletion amplifies the stress response, creating a self-reinforcing cycle that progressively worsens with age. The consequence for sleep is direct. Elevated evening cortisol suppresses melatonin secretion from the pineal gland, delays sleep onset, reduces total sleep time, and dramatically reduces the proportion of slow-wave sleep, the deep restorative stage that the brain requires for memory consolidation and cellular repair. Consider this for a moment. Every night that sleep is fragmented, the body produces less growth hormone, because growth hormone is secreted almost exclusively during slow-wave sleep. Less growth hormone means slower cellular repair, reduced muscle preservation, and accelerated biological aging. The insomnia is not merely an inconvenience. It is a compounding mechanism that accelerates the very processes it is the symptom of. Mechanism 3. The NMDA receptor and nocturnal hyperarousal. This is the mechanism that sleep medicine has been slowest to incorporate into clinical practice, and it may be the most consequential. The NMDA receptor, N-methyl-D aspartate receptor, is the primary receptor for glutamate, the brain's main excitatory neurotransmitter. Under normal conditions, magnesium ions physically occupy the NMDA receptor channel, acting as a voltage-dependent block. They prevent excessive glutamate stimulation by physically blocking the channel until a sufficient depolarization signal justifies opening it. This is called the magnesium block, and it is one of the nervous system's most elegant regulatory mechanisms. When magnesium is depleted, this block is removed. The NMDA receptor becomes chronically sensitive to even low levels of glutamate activity. The result is a state of sustained cortical hyperexcitability, a background level of neural activation that does not quiet at night. Sleep scientists refer to this condition as nocturnal hyperarousal, and a growing body of research identifies it as one of the primary neurobiological signatures of chronic insomnia in older adults. A landmark study published in Sleep Medicine Reviews in 2019 specifically examined the magnesium-NMDA connection in aging populations, finding that the age-related decline in neuronal magnesium concentrations directly correlates with increased nocturnal EEG activity in the beta frequency range, the brainwave pattern associated with alert, active wakefulness during what should be deep, slow-wave sleep. Before continuing, if this level of research clarity is what you have been searching for, subscribe to Golden Glow Senior right now and turn on notifications. This channel publishes evidence-grounded content like this every week, specifically for people over 50 who take their health seriously. Subscribe now, and let us continue. Mechanism 4. Melatonin synthesis, the magnesium, serotonin-melatonin cascade. Melatonin does not arise spontaneously at night. It is the endpoint of a precise biochemical cascade that begins with the amino acid tryptophan and proceeds through several enzymatic steps, each of which requires cofactors, including magnesium. Tryptophan is first converted to 5-hydroxytryptophan by the enzyme tryptophan hydroxylase. It is then converted to serotonin by aromatic L-amino acid decarboxylase, a pyridoxal phosphate-dependent enzyme in which magnesium plays a supporting role. Finally, serotonin is converted to melatonin in the pineal gland by arylalkylamine N-acetyltransferase, AA-NAT, the rate-limiting enzyme in melatonin synthesis, whose activity is modulated by intracellular magnesium concentrations. When magnesium is insufficient, the entire upstream cascade is impaired. Less serotonin is synthesized, less melatonin is produced. The circadian signal that the brain uses to initiate the biological transition into sleep becomes weaker. The darkness of the room may change, but the biochemistry does not follow. If disrupted sleep has been unexplained for years, despite good sleep hygiene, despite careful management of light and schedule, what comes next finally provides a cause that conventional assessments consistently miss. Mechanism 5. Skeletal muscle physiology and sleep fragmentation. There is a less discussed but clinically significant pathway through which magnesium depletion directly fragments sleep in older adults, one that operates not through the brain but through the muscles. Magnesium and calcium are physiological antagonists in muscle tissue. Calcium ions trigger muscle contraction. Magnesium facilitates relaxation by displacing calcium from its binding sites on the myosin crossbridge. In a well-mineralized body, this balance ensures that muscles fully relax between contractions. When magnesium falls, calcium's contractile signal goes partially unopposed. The result in skeletal muscle is a persistent low-grade hypertonicity, an inability to fully relax. Clinically, this manifests as the nocturnal muscle cramps that affect a substantial proportion of adults over 60, as well as the subtler phenomenon of restless legs, an uncomfortable, movement-seeking sensation in the lower limbs that arises precisely during the transition into sleep. Research published in the Journal of the Orthopedic and Sports Physical Therapy in 2020 confirmed that magnesium supplementation significantly reduces the frequency and severity of nocturnal leg cramps in adults over 60, with effects measurable within 2 weeks of consistent supplementation at clinically appropriate doses. The most important element of this entire presentation is still ahead, because understanding these 5 mechanisms is only meaningful if it is translated into a precise, structured protocol. And that protocol contains one detail that most general recommendations overlook entirely. A detail that determines whether supplementation actually corrects intracellular deficiency or merely affects serum levels without reaching the cells that need it most. The evidence-based protocol for correcting magnesium deficiency in adults over 60 requires attention to 3 variables: form, dose, and timing. Form. Not all magnesium supplements are equivalent. Magnesium oxide, the most commonly available and lowest cost form, has a bioavailability of approximately 4%, meaning that the vast majority of each dose passes through the gastrointestinal tract without being absorbed. For sleep specifically, the 2 forms with the strongest evidence and highest bioavailability are magnesium glycinate, in which magnesium is bound to the amino acid glycine, itself a sleep-promoting compound that reduces core body temperature and enhances GABA activity, and magnesium threonate, a form specifically developed to cross the blood-brain barrier and raise neuronal magnesium concentrations. A study published in Neuron in 2010 demonstrated that magnesium threonate was the only form tested that produced measurable increases in cerebrospinal fluid magnesium levels. Dose. The current recommended dietary allowance for magnesium in adults over 50 is 420 mg per day for men and 320 mg per day for women. Most adults over 60 consume fewer than 250 mg per day through diet. A therapeutic supplementation dose of 200 to 400 mg of elemental magnesium from a high bioavailability form, taken daily, is the range supported by the clinical literature, including the Journal of Research in Medical Sciences trial, cited at the opening of this video. Timing. Magnesium's effects on GABA tone, NMDA blockade, and cortisol suppression are most relevant during the hours preceding sleep. Taking the full dose 60 to 90 minutes before the intended sleep time is the optimal strategy for leveraging its neurological effects. Do not take magnesium with calcium supplements, as the two minerals compete for absorption. Week-by-week expectations. In the first week, the most noticeable changes are typically in muscle relaxation, reduced nighttime cramping, and a general reduction in physical tension before sleep. By weeks 2 and 3, sleep onset latency typically begins to improve. The time required to fall asleep shortens. By weeks 4 to 6, deeper and more sustained sleep, as indicated by reduced nighttime waking and improved morning alertness, becomes consistently evident. For those using magnesium threonate specifically, cognitive clarity improvements have been reported in the 4 to 8 week window, consistent with rising neuronal magnesium concentrations. Think about your own sleep patterns tonight. The fragmentation, the early waking, the mind that will not quiet. These are not simply features of aging. They are, in significant measure, the measurable biological consequences of a correctable deficit. And correction is within reach. Before closing, if today's research gave you something genuinely useful, share this video with one person in your life who is navigating the same challenge. And if you have not yet subscribed to Golden Glow Senior, do that now and turn on notifications, because the research published here next week may be just as important as what you heard today. 3 things to carry forward from today. First, magnesium deficiency after 60 is not a fringe concern. It is a structural consequence of aging biology, medication burden, and declining dietary intake, and it disrupts sleep through at least 5 distinct and clinically validated mechanisms. Second, a standard serum magnesium test will not reveal subclinical deficiency, because the body maintains serum levels at the expense of intracellular stores, making the symptom picture itself the most reliable diagnostic signal. Third, form, dose, and timing matter. Magnesium glycinate or threonate, taken at 200 to 400 ml of elemental magnesium 60 to 90 minutes before sleep, represents the evidence-based starting point. The biology of sleep is not fixed by age. The pathways that permit deep, restorative rest remain intact. They are simply waiting for the molecular conditions that allow them to function. That is not a hope. It is what the research shows.